Hi, everybody. Thank you so much for joining us today for another session of EI Live K-12, brought to you by the Earth Institute at Columbia University. My name is Cassie, and I'm the director for the Office of Education and Outreach. And a big part of my job is to bring our scientific research to different audiences and communities, including K-12 students and educators. So for those of you who are joining us for the first time and aren't familiar with the Earth Institute, our core mission is to foster a greater understanding of the science behind sustainability and the climate crisis, as well as what we as global citizens can do. Experts make up the Earth Institute include economists, business and policy experts, earth scientists, specialists in public health and law. And the Institute is actually made up of more than 24 research centers and several hundred people who collaborate across many different disciplines and departments within Columbia University. What we're hoping to do with these sessions is to introduce you to our interdisciplinary work through our experts. We're going to have these EI Live K-12 sessions until the end of June. And if you'd like more information on that, please contact me directly. So today we're going to hear from Janine Birbaum, who is a PhD candidate at lamont-doherty Earth Observatory, which is one of those Earth Institute research centers. And today she's going to help us better understand the different types of volcanoes, the processes that lead to volcanic eruptions, and the relationship between volcanoes and plate tectonics. So for our attendees, we are going to be only using the Q&A box. So as a reminder, it should be used if you have questions for the presenter. Janine is going to be doing her presentation, and when her presentation is done, she's going to we'll turn it over for questions. You're free to type in a question in the Q&A box at any time, and we'll be monitoring that throughout, and we'll make sure to get all of your questions answered. Once our session is done today, we're going to share a link with everyone who registered for the event so that you can access our recording later on. We do take a few days to get the video. We edit the video and then we post it to YouTube. So please give us, we usually are able to send it out by early next week for our Wednesday sessions. Again, if you have any questions or technical difficulties, that is not a question for our presenter, please email me from the email that I shared link for the session with you at. So without further ado, I will turn it over to Janine.
Thanks, Kathy. Can you see me and hear me?
Yep, great.
Great. Yeah, thanks everybody for coming. I'm excited to talk to you guys today about volcanoes. So to just give you a little bit more background on me, I study physical volcanology, which means that I think about the physics and the dynamics of how volcanoes erupt, how they behave, and I do that using a combination of lots of different techniques. So some of those things are computer simulations, like this video that you can see at the bottom. Sometimes I work in the lab with what we call analogs, so things that behave like miniature volcanoes, since we can't always do experiments at the full scale of a volcano. And as you can see, sometimes that ends up getting a little bit messy, but it's a lot of fun. And then also I get to work with field data that people collect at active volcanoes. So we're combining lots of different approaches to try and understand one problem. So to start off, what is a volcano? A volcano is a vent in the Earth's crust through which lava, steam, and ash are expelled. So normally we think about it in sort of this cross-sectional view on the left, where we have rock that's hot deep in the earth at the mantle that begins to melt, can move its way up into the crust. Sometimes it stays there for a little while in a magma chamber, and then it can erupt out the surface through a vent and release lots of different what we call eruptive products. So some of those are lava. We can see a video, hopefully, of some lava. This is from Kilauea Volcano in 2017. And we can see that it sort of oozes this sort of gooey, viscous lava. And so these are typically what we would call something like an effusive eruption, where lava is just sort of slowly oozing out of a volcano. And you can see here where it's red, that's where it's hottest, and where it's dark is where it's cooled a little bit. And even in some places is solid. It's cooled enough that it's a solid here at the sort of outer rind. And sometimes volcanoes can release ash and steam or other volcanic gases. This is a video of what we would call an explosive eruption, where lots of ash is being produced. You can see this dark color. It's a little bit like you might see smoke from a fire, but instead of being burned pieces of wood, it's actually little teeny tiny pieces of rock. So the difference between an effusive and an explosive eruption, we can see is very different in what comes out and how fast it moves and where it's going to travel. So this is a big question when we're looking at volcanoes, is an eruption going to be effusive or explosive? And as we'll see throughout the rest of the talk, different types of volcanoes are more likely to have one type of eruption or the other. So I also said that there's gas coming out of volcanoes. What gases are they? Sometimes they're steam, so hot water, but sometimes they're carbon dioxide, and lots of other sort of nasty things like sulfur and fluorine and chlorine. And something that you might hear people talk about sometimes is the contribution of volcanoes to processes like global warming. And are volcanoes really accelerating global warming? Are they releasing enough carbon dioxide to make a difference to the atmosphere? And so yes, volcanoes do release carbon dioxide, but they only release in a given year about 1% of what we produce through anthropogenic sources of the burning of fossil fuels. Similarly, they produce a lot of sulfur, which can be a pollutant that decreases air quality in cities. And here on the right, what you can see is that all of these little colored areas are places where a satellite has measured sulfur. And lots of these are coming from volcanoes. So here, Carancini or Krakatau or Merapi, we can see those are acting as what we call a point source. So they're releasing a lot of sulfur. And we can see them in comparison to a city like Singapore, that a single volcano can have a lot of sulfur. But again, on the global scale, they're only releasing maybe a quarter or a third as much sulfur into the atmosphere as human activity. So we'll start with our first activity today, which is a question about where are volcanoes? And I want you to find the volcano that's closest to you. So there's a couple links here that you can check out maybe afterwards. This top one takes you to a USGS website that will show you the currently active volcanoes in the US. And the second one takes you to a website from the Smithsonian Institute, which will show you globally all the volcanoes that are erupting right now.
Janine, I'm just going to interrupt for a quick second because we did have a question about sulfur in the air. When you were talking about the release of sulfur in the air, and the participant was wondering if it was bad to actually, and was it bad for your health to breathe in sulfur when it's released?
Yes, it can be bad for your health to breathe in volcanic gases, both the sulfur and the other halogens, so fluorine and chlorine can all be bad to breathe in. And also they often come out in acid rain and they can land on crops. So there are reports of volcanic eruptions where the gases that came out of the volcano landed on crops and were bad for livestock, that livestock died.
Okay. Great, thank you. And we just had a question about the websites, and we will definitely share all the links that are mentioned in this presentation. So thank you.
Great, yeah. So if you follow the Smithsonian Institute, so that's the second link there, you'll get a map like this. I pulled this just yesterday. So these are all of the volcanoes in the world here marked with little volcano symbols that are erupting right now. And so the closest one to you, depending on where you are, I'm here on the East Coast, so the closest one to me here is in Central America. This is Nevada del Ruiz, I think, in Costa Rica. But you might be closer to Cleveland, which is up here in the Aleutians. But actually, we're gonna do a little exercise to help you find the nearest volcano. So if you follow this link up at the top, right now, it'll take you to a little piece of code that we can use to find the nearest volcano. So I'm actually gonna pull up my screen as well with that link. So if you can see here, if you follow that link, it will take you here, and I definitely encourage you to do that. So this is what we call a Jupyter notebook. This is something that a lot of scientists might use to perform analyses on data or to visualize data, so to plot it and look at what it looks like. And there's a couple different files in here. We're going to click on this top one called nearest volcano. And what this code does is I can put my location. I've already put in the location for the Lamont-Doherty Earth Observatory as my lat and my lon, but you can find your own coordinates by going to Google Maps and finding your latitude and longitude. And then if I just hit run a couple of times, what this script is going to do, it's going to tell me that the nearest volcanoes, this is a database of all the volcanoes that have been active in the last 10,000 years that I got from the Smithsonian website. And it's going to tell me that Saba is the nearest volcano to me, and it's 1,735 miles away from me. So here I am at the blue dot, and you can see this yellow triangle here. That's the closest volcano to me, Saba. But of course, this volcano is not erupting right now, but it has been erupting sometime in the last 10,000 years. We can zoom in a little bit and see that it's here in the Lesser Antilles. So I think that might be surprising for a lot of people. If you live on the East Coast, the closest volcano to you probably is in the Lesser Antilles and not actually in the United States. But of course, if you're on the West Coast, there are lots of volcanoes in the United States, about 169 in the US. And does anybody know which state has the most volcanoes? Can they answer in the Q&A?
Yeah, we could definitely give our participants a chance to answer. And while they think about the state that might have the most volcanoes, there was a quick follow-up question to when you talked about livestock and sulfur release. So the participant was wondering how much livestock are actually affected or killed by chemicals from a volcano every year.
I'd say in most years, probably none or maybe a couple dozen. Most of the time, eruptions only impact livestock that are very close to the volcano. And lots of people do live near volcanoes, but in a general year, most livestock aren't close enough to a volcano to be affected. But in years that we have big eruptions, hundreds or thousands of livestock can be killed.
Okay, great, thanks. And I'm going to squeeze in one more question here while we wait for additional folks to maybe chime in about where they think which state has the most volcanoes. There was a question about how high does an eruption go when a volcano erupts?
That's a great question. So it depends on the type of the eruption. So in effusive eruption, like we saw before, where the lava is coming out, the lava might only get a few meters to a few tens of meters, maybe 100 meters in the air. But a big eruption can go tens of kilometers into the atmosphere. So maybe 20 or even 30 kilometers for a really big eruption.
Great, thanks. So it seemed we have one answer about which state, and someone says Colorado. How close?
Yeah, so Colorado does have a couple of volcanoes.
Alaska, there's another one.
Yeah, so Alaska is the correct answer. Alaska has more volcanoes than any other state in the US. And most of them are here, you can see in the Aleutian Island chain, which is entirely made up of volcanoes. All right, so I'm going to go back to the presentation that we had before. Okay. Yeah, so here's that zoomed in map again. And I think it'd be good for us to take a second and just make a note to yourself about any observations that you might have about these volcanoes. And one of the things that I see when I look at this map, and lots of geophysicists have noted in the past, is that these volcanoes are not randomly distributed, right? So we can see places where there's lots of volcanoes all in a line along sort of all of the west coast of both North and South America, places like Japan, and there are not as many in sort of the interiors of continents. So think about why that might be. I'm just going to give you the answer, which is plate tectonics. Everything in geology and the earth sciences always comes back to plate tectonics. And so if we look at the boundaries between different plates, like here along the Pacific plate, sometimes called the Ring of Fire for how many volcanoes are around it, we see that our volcanoes are mostly concentrated along the edges of plates. So does anybody, can anybody name the 3 types of plate boundaries?
So we're going to give our, I think we'll give our audience a little bit of time to see if they can name the 3 different types of plate boundaries. So we did have some questions, actually, if you could go back to the map that you had pulled on. Yeah, so we had sort of two viewers who are wondering, you know, based on where they live or where they're from, what the closest volcano is actually to Atlanta, Georgia. And then the other question was, what is the most dangerous volcano in Italy? We have a participant who's Italian, so.
Sure. Yeah, so the closest one to Georgia in terms of like what's erupting right now would probably also be here in Central America. The same as on the East Coast. I'm not sure, you know, which of these is the closest. It's probably one here in Mexico would be the closest. If you look after the after this slideshow is over, you can go back to that link and you can find your coordinates for Atlanta, Georgia, and you can plug them in and the script will tell you which one is the closest. In terms of Italy having, which is the most dangerous, you know, I don't really know. There are lots of volcanoes in Italy and different volcanoes pose a different sort of danger, right? So if we're thinking about sort of the potential for a big eruption having widespread impact, we might care more about what's the name of it? There's like a volcanic field that lots of people live on that's been experiencing a lot of uplift and subsidence. But also, I mean, there are historical eruptions, right, like Vesuvius that has killed people. And there are lots of volcanoes that are more active that people do die on occasion. But I don't know which one would be the most to be worried about in Italy. I'm not an expert on Italian volcanoes.
All good. Yeah, and we'll definitely, just a reminder to viewers that we'll share the My Binder link as well, so that you can go in and you can look up the coordinates of your own location and find out which ones are the closest volcanoes to you. So Janine, we have an answer to your question, and the different types of plate boundaries, convergent, divergent, and transform boundaries.
That's perfect and exactly right. So here we're going to switch to a cross view section of sort of an idealized plate tectonics boundary that shows us all the different kinds. So here's our convergent margin at our subduction zones here. And one of the things that we can see even labeled on this diagram is that we have the generation of melt occurring above subduction zones, both in the continental both under the continental crust and under the ocean, which would result in big mountain chains or island arcs. We also have divergent boundaries right here, ocean spreading centers, and we're showing again some magma being generated there. We have some transform boundaries labeled here on our diagram, and we also have hotspots, which we're going to talk about a little bit. So we'll talk about the different kinds of volcanoes that occur at these different plate boundaries in more detail. So we'll first look at convergent margins. Often these are called sort of arc volcanoes because they make a big long arc if you look at them on a map view. And some famous examples here we have on the left, Mount St. Helens, and on the right we have Mount Fuji. And both of these, and typical of arc volcanoes, are what we call stratovolcanoes or stratocones. Sometimes they're also called composite volcanoes. And when we look at these in cross-section, we can see why they're called stratovolcanoes. So strato meaning layers. So they're made up of lots and lots of layers of, in white here, ash that have come out of an explosive eruption, right? And in these darker places, we have lava flows. So do we think that, whoops, well, I guess you've seen the answer now, is that are these stratovolcanoes mostly made up from effusive or explosive eruptions? And the answer is that it's a little bit of both, right? That we have alternating periods of explosive or effusive eruptions, and that gives us these stratified layers of ash and lava building up over time. And so we already saw the sort of explosive eruption of Mount St. Helens, and an example of a more effusive eruption happening at that same volcano is that this is a lava dome that grew inside the caldera of the Mount St. Helens eruption. So this would have been in 1980, this would have been in the 2000s. And you can see it kind of looks like sort of you've squeezed toothpaste out of the tube and just squirted out a little bit of lava here at the surface. So we can see both types of eruptions happening just at one volcano. So next we're gonna talk about divergent plate boundaries. So this is places where the plates are moving apart. So most of that is occurring at mid-ocean ridges. So we do see volcanoes on mid-ocean ridges and spreading centers. They're a little bit harder to find sometimes because they are under the sea, so we can't go and look at them. So the most famous example of what we call a submarine, right? So under the ocean volcano is this one called Axial Seamount, which is just off the coast of the Pacific Northwest on this little tiny part of the spreading center between the Juan de Fuca plate and the Pacific plate, right up here labeled in purple. So this is a pretty famous volcano. It sort of goes through these cycles of activity that we can see it almost breathing, where it inflates as magma comes in, and then sometimes a little bit of magma will come out, it'll have an eruption, and it'll deflate again. So it really does look like it's breathing as gas and magma accumulate in the chamber and are released. And so one of the kind of interesting things that happens only in the submarine environment are what we call black smokers. So they're a type of hydrothermal vent. Hydrothermal vents occur on all types of volcanoes where hot fluids and gas are being released out of the ground, where groundwater usually is interacting with magma in a magma chamber and then moves up to the surface. And when they're underwater, they form these really cool chimneys called black smokers. And one of the surprises upon finding these in the ocean was that they're actually teeming with life. Even though they're kilometers under the ocean, it's dark, there's no light coming in, so there's no photosynthesis that can happen, but there are all these communities that have unique adaptations to be able to live on black smokers. You can actually see some in these photos, these little white crabs that have no eyes because there's no light to see anything. But there's also lots of worms and different kinds of bacteria and archaebacteria that live only on these black smokers. So what does it look like when the plates are moving apart up on the surface? So we don't have any sort of pure examples of what a mid-ocean ridge would look like if it were happening on a continent, but we have the beginning of one. So in Eastern Africa, we have a spreading center where there's this big line you can see sort of dashed in here, where the continent is being ripped apart. And in another, tens of millions of years, this will be a new ocean. But right now it's just starting. And so the volcanoes are still on the surface. And so it's easier for us to go and look at them. And we can see an example here of a volcano called Erta Ale, it's labeled on this map, right up by the Red Sea. And we can see these two big holes in the ground where steam is coming out. There's actually lava inside of this, called a lava lake. And we can see that they have sort of a very different shape than the stratovolcanoes we looked at before. So they have this very low profile. You can see this dark patches where there's this fresh lava here. And some of the volcanoes in East Africa are really super special. Whoops. Sorry, I've lost my screen here. I don't know what you guys are seeing. So this is a video from Olduvai Lengai volcano, which has a special type of lava that we call a carbonatite that's super runny. So it almost looks like water when it flows. So we'll just watch it for a second. So this can only occur on the continents underneath the big slab of continent where there's eruptions happening. You can see it flowing. This is in real time. It's not sped up at all. So rather, unlike the sort of ooey gooey lava that was very viscous we saw before, this is much thinner and can run almost like water. And you can see somebody's boot here. This lava is not red because it's not nearly as hot as the lava we were looking at before. So you can go right up close to it.
Janine, since you're talking about the lava temperatures, we did have a question about how hot lava is, and I think so. We've gotten some great questions, so I might jump in at certain times and just ask you. But since you're talking about the temperature, could you elaborate on perhaps? I'm assuming the answer has to do with it's different types of lava, different types of temperatures. But yeah, it'd be great if you could answer that question for us.
Mm-hmm. Absolutely, yeah. So different types of lava, as you said, have different temperatures. So lavas that might occur at the stratovolcanoes we saw before, those usually have what we might call a more evolved composition. So those magmas have sat around in the crust for a long time. And as they get older and they get more mature, they change. And so they become more silicic, so more rich in things like quartz. And the eruption temperatures usually go down. So for a silicic eruption, lava temperatures might be somewhere in the range of maybe 700 to 900 degrees Celsius. But lava like you might see at Hawaii might be much hotter, over 1,000, maybe 1,100 or even 1,200 degrees Celsius. So I guess we can move on to the next slide, maybe. All right. Yeah, so we've talked now about convergent margins, so arc volcanoes occurring at subduction zones, and we've talked about what happens at divergent plate boundaries, so both mid-ocean ridges and also when we have spreading happening underneath continents. We're not going to talk anymore about transform fault boundaries because transform plate boundaries don't usually have any volcanoes around them. There's no way for magma to be generated, so they don't usually have volcanoes. But we will go on and talk a little bit more about hotspots. So this is a place where the mantle underneath the place is especially hot, and so it's buoyant, kind of like in your lava lamp. When it heats up, it can rise. So then the magma can come up underneath these hotspots and make particular kind of volcanoes. So underneath hotspots, we're generating some of that fresher and less evolved magma. So like I said, it's the hotter kind, and it's usually this black color, and it erupts in sort of two different styles. So one of them would be fissures. We can see on the right here, this sort of long chain of mounds, or what we would call a fissure eruption. This is from LavA volcano in Iceland. And on the left, we have the Halemaumau lava lake, or the lava lake that was in the Halemaumau crater at Kilauea volcano that existed until about 2 years ago when it was drained during the big eruption there. And Hawaii volcanoes are sort of the classic example of what we would call a shield volcano. So a shield volcano, again, is made up of layers, but instead of having these alternating layers of ash and lava, like we saw in the stratovolcanoes, they're just layers of lava. And because the lava can sort of flow far away from the vent, they get these sort of characteristic low slopes and low profiles, but they can grow to be really, really big. So we can see here an example of sort of the scale of different volcanoes. We have on the left our composite volcano, that's Mount St. Helens that we already looked at, and comparing that to a shield volcano like Mauna Loa, we can see just how much bigger Mauna Loa is in comparison, right? Much, much bigger eruptions, or much bigger volcanoes. So if these are mostly made up of lava, do we think that they're mostly effusive type eruptions or explosive eruptions?
So while we give our participants a chance to answer whether it's effusive or explosive, there was a question about if you happen to come in contact with the magma in a volcano, you know, how badly can you burn, and can you actually die from injuries and burns for the magma?
Yeah, so most of the time people don't die from sort of effusive eruptions or like lava flows, usually because the lava moves slow enough that you can get away from it. So there are few recorded deaths and injuries from lava flows. They're really hot, so most of the time you wouldn't even want to get close enough to one that it could hurt you. Sometimes when they flow really fast, they can, you know, flow into people's homes, and if people, especially if it was in the middle of the night maybe, were still in their homes, if they didn't know the volcano was going to erupt, people do die from lava flows, but it's very unusual. If you were to, say, fall into a lava flow, yeah, you would probably die. But actually, most of the danger to human lives that we see during eruptions comes from explosive eruptions. So when we saw that big cloud of like ash, the material that comes out of the volcano, the ash and the hot gases, can burn you and can kill you, and they move really fast. So people do die, for example, if they get caught in what we call a pyroclastic flow, which would be when you have that ash coming at you.
Actually, yeah, that was one of the other questions, what is a pyroclastic flow?
Yeah, so pyroclastic, it means pyro means fire, right? And clast is like a piece of something. So these are times when ash and hot gas have mixed together, and they're so dense that they kind of flow like a fluid, even though they're a mixture of gases and solid particles. And they can flow down slopes, and they are one of the bigger dangers for people within a few kilometers of a volcano center during an eruption.
Okay, great. Thanks for answering those questions. So it looks like most of our participants have said effusive, and one has said explosive.
Mm-hmm. Yeah, so they are mostly effusive, but actually not always. So even shield volcanoes like Hawaii can have explosive eruptions, but you're right that most of the time these ones that are made up of lava flows, they're mostly effusive. So then we're just going to look at one more sort of size comparison of how big shield volcanoes can get. So here on the right we have sort of the shape of Mauna Kea, which is another shield volcano in Hawaii, and we're going to compare it to the size of Everest. And so while we know that Everest is the highest volcano, or a highest mountain, sorry, it's not a volcano, the highest mountain on Earth, it's actually not the tallest. So if you measure from the top to the bottom of the edifice, Mauna Kea is actually about 1.5 kilometers taller than Everest. So Mauna Kea, sometimes we will tell you that it's the tallest mountain on Earth. And here it is in comparison to Olympus Mons, which is quite a bit bigger, but you know, not sort of orders of magnitude. Maybe it's, you know, only you know, maybe 4 or 5 times taller than Mauna Kea. And Olympus Mons is the biggest volcano in the solar system. So it's on Mars. We have volcanoes on lots of other planets, including Earth. There are also volcanoes on Venus and Mars and Jupiter's moon, Io. They occur throughout the solar system. And so just to show you the scale of like how big volcanic eruptions really can be, there's a special type of volcanic eruption that we call a large igneous province, sometimes called LIPS for short. And these are places that there's way more material that comes out than occurs at, you know, usually hotspots or anything like that. So way, way bigger than Mauna Kea. But we've never seen an eruption like this happen. They've only happened long ago in the past. So here's a map in the top left, maybe you can't see it very well, that shows you where all of the large igneous provinces are, just in different colored swatches. And here's a picture of what they look like. So these are huge outpourings of lava that form many, many layers, and they cover huge areas. And actually, like I said in the very beginning, that volcanoes only let off a little tiny amount of carbon dioxide compared to human activity. When we look in the past at these large igneous provinces, some of these may have been big enough to really generate a big climate impact when they erupted. And so on the right here, we have a plot that's showing us on the x-axis, millions of years before present. So here on the left would be 300 million years ago, so a long time ago, back in the Paleozoic. And then on the right, 0 would be now, right? And so most of this is the Mesozoic, so at the time of the dinosaurs, right, in the Triassic, Jurassic, and Cretaceous. And then on the y-axis, we have the percent extinction. So this is how many genuses went extinct during a given time period. And so what we see, these big spikes, are what we call mass extinction events. This is when lots and lots of organisms are dying and we're wiping out not even just species, but whole genuses. And each of these big spikes, we can see all the big ones and some of these smaller ones line up with these pink bands that tell us when there was the eruption of a large igneous province. So some of these, we think, or scientists think generally, that the eruptions might have caused mass extinction events. And so we can look at these in the past and try and understand what having a sudden influx of a large amount of carbon dioxide or other volatiles does to our atmosphere, to try and understand the changes that are happening now. And then talking more about sort of big volcanoes, there's another type of big volcano. So we're still thinking about hotspots, but now instead of hotspots being underneath the ocean, like in Hawaii or in Iceland, which is both hotspot and divergent plate boundary, when we think about what happens to hotspots underneath continents, we can think about Yellowstone as being a particularly famous example of a hotspot underneath a continent. And Yellowstone, that volcano is so big that there's not even anything to look at when you go to visit it. It's what we call a caldera volcano, which is when an eruption was so big, so much magma came out that the ground around it just fell into the pit of what was left of the magma chamber. And the caldera at Yellowstone is so big that it's hard to recognize that it's a volcano at all. And so this is a picture here of Grand Prismatic Hot Spring at Yellowstone, which is just one of many hydrothermal features that occur inside the caldera. And again, it's host to a lot of organisms that have special adaptations to be able to live in these hot waters. And so the question I have for you is, do caldera type volcanoes, where we've evacuated this huge amount of material, Are they explosive or effusive? And I'll give you sort of this diagram to look at while you ponder that question. So this is a map of the United States, and each of these dashed lines shows you where the ash from different eruptions landed. So you can see that from Yellowstone, which are these 3 pink layers, 3 different eruptions, and the ash covered half of the continental US. And then here in brown is a similar size eruption from the Long Valley caldera in Eastern California. And in comparison, the ash that came from the Mount St. Helens eruption looks really tiny compared to how much ash came out during the Yellowstone eruptions. So do we think these eruptions were effusive or explosive?
Okay, so we'll give our participants a little bit to think about there. So while we're there, I will ask a question. I'm going to combine sort of 2 questions because they're both related to size. And so participants have been wondering, you know, how big volcanoes can actually get. And I'm assuming there's different ways, you know, of measuring of that, or, you know, there's some examples that you can share with us.
Sure. I mean, we saw sort of in the previous diagram a few slides back, the size of like Mauna Kea being, you know, 10 kilometers tall from its base on the ocean floor to its top. That's the biggest volcano on Earth. And for comparison to that, you know, we saw that our stratocones are quite a bit smaller. But you're right, there are different ways to measure it. If we measure it based on, for example, the height or the volume of the magma that came out. And so the biggest volume eruptions, or the biggest volume, I suppose, volcanoes we would call them, would be these large igneous provinces where the magma is huge. So the biggest one there would be, you know, depending on how you count it, I would say the Central Atlantic Magmatic Province, sometimes called CAMP, that happened about 200 million years ago. And the lavas from that eruption, you can find them all up and down the east coast of both North and Central America. You can find them in Africa, you can find them in Europe, because they happened when the Atlantic Ocean was first opening up. So there's lava on both sides.
Great, thank you. So we have a couple of answers. So I think most people have said explosive, although we have a few who have said effusive.
Yeah, I mean, again, that balance is about right. So they are mostly explosive, which of course is why we see ash going really far away. But most of these eruptions also have an effusive component. So here on the right, this figure that's just arrived is the lava flows that are mapped at Yellowstone. So these are an effusive part of effusive eruptions at that same volcano. So most volcanoes kind of have this mix of effusive and explosive, but we saw that the balance can change, right? So with our stratocones having a good mix between the two, shield volcanoes having mostly effusive, but sometimes they can have explosive activity, and our caldera eruptions being sort of the opposite, where they're mostly explosive, but they also have this effusive behavior sometimes. And so now that we've talked really about all of these sort of concentrated places where we have lots of volcanoes, right? We've talked about plate margins. We've talked a little bit about hotspots like here at Iceland or Hawaii. But we do see that in a few cases, there are volcanoes that don't really seem to line up on that boundary. Some of them sort of in the middle of Africa or in the sort of western part of the US. Sometimes there are volcanoes that really don't seem to be on a plate boundary or necessarily with a hotspot. And so these are what we would call intercontinental, just meaning within the continent. And these have their own sort of typical behavior. And one of the interesting things is that unlike at some of these places where all of the magma is focused and you have many, many eruptions coming out of one vent, in these sort of intercontinental cases, we get what we call distributed volcanism. So it's volcanism that happens over a big area, and in each eruption, the vent location changes. So what you can see here, this is SP crater in the San Francisco volcanic field in northern Arizona. And we can see really here a very classic cinder cone shape, right? And a lava flow that was associated with that. But we can also see another cone over here, and another one over here, and another one over here. And the more and more you look, the more that there are just hundreds of these things, and they're all tiny. And so all of these, the idea is that there's one eruption happens, it forms one little cinder cone, and then the lava moves somewhere else in this volcanic field. So we get these areas where we get just sort of distributed volcanism. So one little eruption here and there. And these are what we call a cinder cone eruption because they're made up of little tiny pieces of rock. They're not as small as ash usually, they're a little bit bigger. You might call them cinders, and they form this nice cone shape. And sometimes we also call these fields, sometimes they're also a place for bimodal volcanism. So two kinds of volcanism happening together. So we talked a little bit about composition happening as a magma matures. As it gets older, it changes from one side being the basalt to the other side being a rhyolite. And sometimes in some places we see sort of a smooth transition between those two things. But in intercontinental settings, we get one end member and the other. So we got two modes in our composition and nothing in the middle, which is a little bit of a mystery. They're kind of interesting, and a lot of scientists are interested in why do we only see these sort of two different types of magma and nothing in between. So that's the end really of these prepared materials. I just want to leave you guys thinking about, we've looked at where volcanoes are, the different kinds of volcanoes that occur at our different plate boundaries. They're controlling mostly where the volcanoes are. And we've covered sort of all the basic types of the volcanoes. So we saw fissure and shield volcanoes occurring at our hotspots under the ocean mostly. So these are unevolved hot magmas that are really runny and mostly have effusive type eruptions. We saw both domes and stratovolcanoes occurring in arcs, where we have these alternating things where we have sometimes ash or sometimes magma. And of course, the dome volcano is just lava all the time. And we saw cinder cones in our intercontinental places, and we also saw calderas over the big hotspots on the continents that were very explosive. So we'll just end, I'll take your question, the rest of your questions in just a second, but I want to leave you with some questions that we as scientists have about volcanoes that we want to learn, which are things like what controls whether an eruption is effusive or explosive. We saw that lots of volcanoes have a little bit of both. Sometimes they have more of one or the other. But what controls for a particular eruption, which is going to happen? How can we make predictions about when a volcano is going to erupt? A lot of volcanoes show signs that they're going to erupt before they do. So how do we know when that's going to happen? We talked a little bit about the hazards of different volcanoes. So that people or livestock could be hurt or killed during an eruption. So for different volcanoes, we worry about different hazards, and we want to know what can we do if we think an eruption is going to happen to reduce the impact on people around it. And we talked a little bit about sort of feedbacks between volcanoes and changes in global climate. So we saw how volcanoes, maybe these big eruptions, could drive changes in climate. But I think we're also interested in this time of change in our climate system. How are volcanoes going to respond to those changes? So I think that's it for me, and we'll just take your questions now.
Great. Thank you so much. That was fantastic. So we do have a couple of questions. So I think there was a question that I think you answered a bit earlier, but I think if you could, I'm going to tack on a bit of a question to this. So the question was, you know, have people ever died from lava flows? And so, you know, you answered this a little bit earlier, and for I think for my additional question, I would say, you know, what are some of the sort of strategies and practices in place where people who do live, you know, in active volcanic zones to prepare and to make sure that they are prepared in the event of an eruption so that they're not in danger in any way?
Sure. Yeah. So I mentioned that people have died during lava flows, not in the US, but in other places, lava flows have killed people. People do die in eruptions in the US as well, but not usually from lava flows. Um, and in terms of like what we can do is a really hard question because volcanoes are really big and their products are really hard to deal with. So when a lava flow is coming, most of the time what we do is get out of the way. So usually a particular volcano is being monitored by different scientists. There's different volcano observatories all over the US that watch different sets of volcanoes and try and make predictions. And if they think something's going to happen, the best thing usually to do is to move people out of the way. But also we think sort of in the longer term about where are we going to choose to build our schools and our hospitals and our infrastructure and roads and power plants so that they're not going to be in the way of a volcanic eruption if it does happen. There are a few historical attempts to divert lava flows, so to move them away from important structures and to somewhere else. But it's an expensive practice that doesn't usually work all that well and isn't really being done anymore, at least in the US.
Okay, great. Thank you. And this question came up when you were talking about the submarine volcanoes. So what happens if our sea life affected at all and when those eruptions happen? And they breathe in, toxic materials or black smoke or anything like that?
Right. So most of the eruptions, certainly at mid-ocean ridges, are happening very deep under the water. So really the only thing that lives down there is these things that live on like hydrothermal vents and on black smokers. And those communities are specifically adapted to deal with changes in their environment, right? So most of these things, they spread very easily. And so if one little pocket of a community gets wiped out by a lava flow, or if the black smoker turns off, those organisms might die, but the bigger community, the species, are spread out enough that they'll survive. I'm not aware of any issues of sort of the chemicals from an eruption killing a lot of living organisms. Sometimes we see when we have eruptions near the coast that when the ash or the lava land in the water, they actually provide more nutrients like phosphorus and nitrogen to the organisms and the algae things that live there. So sometimes we see actually an increase in the amount of algae right after an eruption as they feed on all of those nutrients.
Great, thanks. So the next question is Andrew from grade 2. How does lava melt so fast?
That's a good question. So actually, most of the time, the lava that's coming out of the volcano comes out already melted. So it doesn't melt very quickly. It's just already a liquid inside the volcano, just waiting to come out. But how does magma or lava melt in the first place? Usually occurs, so normally we think about on the Earth's surface that what controls whether or not something melts is its temperature, right? When you have a piece of ice, right, you heat it up and it turns into a liquid. So that's one of the things that controls whether or not a material melts, but there also a lot of materials are sensitive to pressure. So when we squeeze something down really hard, it becomes harder for it to melt. It wants to be a solid. And so a lot of volcanic melts like lavas and magmas are produced through what we call decompression melting. So it's when a rock that is pretty hot is moving up towards the Earth's surface. The pressure on top of it is unloading, and that can actually cause it to melt just as much as heating it up could do.
Great, and thanks Andrew for the great question. So this came up when the next question came up when you were talking about the Ring of Fire. So why is it called the Ring of Fire?
Yeah, that's a good question. So it's usually called the Ring of Fire because the Pacific Plate is sort of a loop shape And it's one of the few plates that has sort of active boundaries that are producing volcanism on pretty much every side. So when we look at it in the map view, it's not a good map to look at it, cut in the wrong place. Here at the Ring of Fire, right, what we can see is that as we trace all the way around this boundary, there's volcanoes sort of on every side. So the volcanoes themselves make sort of this ring around the Pacific Ocean. So it's named for the volcanoes.
Great. And so this is actually a good question. So I use these terms interchangeably, which is probably wrong, but what is the difference between magma and lava?
Yeah, that's a great question. And I think a source of confusion for a lot of people. So the only difference between magma and lava is that magma is still under the ground and lava is on the surface. So it's magma when it's in the chamber under the volcano, and as soon as it erupts, once that lava hits the air, it's lava now. But in terms of like the difference between the materials is that they're really the same.
Fantastic. Great. I learned a lot today, but one important difference is learning the difference between magma and lava. Thank you for that question.
Yeah.
So we have one more question here, and it is kind of a nice way to kind of summarize and end. Can you determine how old a volcano is? And if so, how do you actually determine that?
That's a great question. And it can actually be really hard sometimes. So all the volcanoes I talked about today are ones that mostly we've seen erupting. And a lot of them, they're built over a long amount of time. But how do we gauge how old they are? It really depends on the types of volcanoes. So some types of volcanoes, we can do different dating on them. So when they're very young, if they've flown over, for example, if you had a lava flow that flowed over wood, sometimes you can do carbon dating. But different kinds of volcanoes, we have different radiometric dating techniques that we use. So like you would date any other kind of rock, but some of them it's really hard. Some of them don't have the right materials in them to do good dating. So for example, the cinder cones that I showed, a lot of those are dated not based on any type of like chemical analyses, but rather by their shape. So we look at how they've eroded over time in comparison to other volcanoes in the area. And if a volcano is more eroded or less eroded, we might say it's older or younger.
Great, thank you. These have been very fantastic questions from our audience, and
Yeah.
thank you for asking. So Janine, any concluding comments that you want to make for our participants before we wrap up?
I mean, I just want to say, thanks for listening. And of course, if you have any other questions, reach out. We're always excited to hear more about, what people are interested in and talk about volcanoes. I love talking about volcanoes. So if anybody wants to reach out with more questions, I'd be happy to answer them.
Perfect, thank you. So we're out of time. So like Janine said, if you do have additional questions, feel free to get in touch with me, and I'll be sure to connect everybody to who has questions to Janine. And we will share all the links that Janine had shared throughout her presentation, so you can kind of play around with a map that she had prepared with your own GPS coordinates to figure out how close or far you are from volcanoes. And we'll send out a recording of this session to everybody early next week at the latest, likely. And we hope to see you for some of our additional sessions later in June. We're doing these on Mondays and Wednesdays at 2 p.m. Eastern Standard Time, and we'll continue to do so until the very end of June. So Janine, thank you so much for taking the time to do this and for sharing a lot of great volcanic knowledge and with us, and this was really great. And we hope that participants had a great time. So thank you, and have a good rest of your day.
Thanks so much.